All right, I'm Doel. I'm going to talk about low-level Haskell optimization, as Ed said. I apologize if I'm kind of sniffly. Ed brought back cold from ICFP and gave it to me, so I've been sick for the past few days. So I thought for the beginning of this talk, I should give kind of a disclaimer of how you should go about optimizing, I think. The first is to make sure that you're using -O. It's surprising how many people forget.
Oh, yeah, that's probably a good idea.
Use a microphone.
Can we turn it on?
Is that on now? Okay. All right, so the first thing you should do if your program is too slow is make sure that you're using -O, because people do forget that. It's surprising, but the second thing you should do is profile to make sure you know which part of your program is actually slow and which you should work on. After that, you should make sure you're using the best algorithm for that part of the that part that you've identified as actually slow. But I'm not going to talk about any of that, and I'm going to talk about how, once you do all that stuff, you look at what GHC is doing and try to make it do something better and generate better code. So the first thing you have to do is actually get GHC to tell you what like the intermediate stuff it generates is. And the stuff that I look at most of the time, you can get information on in the GHC Users Guide section 4.19, and it's got a ton of -D dump flags. And the one that I look at most of the time is dump simple, which gives you the core representation after like all the optimizations have run on it. There's also a level below that called STG, which is a more, I'm going to talk about that later in just a minute here. And that is like the basis for the the machine model of how GHC actually executes your code. And so that can be a little bit clearer if you want to understand exactly what's going to happen, I guess, on an abstract machine level, not a physical machine level, I guess. There's quite a few more. C++ is a level that's underneath STG, but above like assembly. It still talks about like explicit registers and stack stuff. It's I don't look, and you can have it dump assembly and LLVM stuff as well. I don't really look at that. I've never really needed to. Some people do, but I would guess that that would be more for people who are trying to make GHC itself do better stuff. Then you wouldn't want to like just permute your code until it generates the exact assembly that you want. And this is the most important part for a lot of people, I'm sure, is that you can pass this flag called dump to file, and it will generate actual files with all of the stuff instead of spitting it all out to standard output, which is what it used to do. And people like wrote tools around that, but now you can get it to actually spit to a file, and so you can even put this in your Cabal file. So if we look at the thing I have here, I have a flag dump, which is true by default, and I'm dumping the simplified core representation and the STG to files, and then I have like a few files for a library and then an executable that drives them for this talk, and I'm also dumping the simplified core for the executable stuff. So when I Cabal build.
You've lost a column, by the way, on the screen.
I have. Oh, just interesting.
It's fine.
All right. That'll be like line numbers. So.
It's just that stuff, yeah.
So I have these links to dump exe and dump src, and you can see we have a bunch of files in here.
Does it for every .hs file that you have?
Yes, every HS file will get one of these files. So,
Yeah?
yeah?
Head block the bottom line of your terminal.
Oh, well, Okay.
Yeah, just enter.
A little more to the right.
Yeah.
Is that better?
If you slide the right a little bit, you can
Let's
get
go
right
to
on.
very slightly over.
Yeah.
Perfect.
How's that? All right.
Yeah.
Still too low.
Is that better? Wow. Okay.
But it's silly for everyone else.
Okay, and then you get a bunch of stuff that looks like this. And so now I'm going to teach you a little bit of how to read this stuff by talking about the syntax of the STG language, which is similar to the core language, but not quite the same. So STG is basically a functional programming language, a lot like Haskell. It's got literal numbers, 0, 1, 2, variables, and most of the variable lists, like when you apply functions, are grouped together like tupled style. So they don't look curried, but they are curried, and you can like apply to as many things as you want. It's just that at this level, it gets kept track of so that it can optimize things better. And then there's like premops like addition and multiplication on machine words and stuff like that. In STG, though, you never have, like lambda expressions are not actually expressions per se. All lambdas are given as bindings to a variable. And there's actually 2 variable lists for every lambda. The one that comes before the lambda specifies all of the free variables that lambda captures, and the one after is all of the arguments to the lambda. And you give lists of bindings of variables to these lambda forms. And then there's this extra annotation here which tells whether when it evaluates the lambda form, if it should write back for lazy evaluation, but I guess probably don't need to worry about that very much right now. And then the expressions are, you can let a bunch of bindings, you can let a bunch of recursive bindings. So regular let, when you see let, things are not in scope in themselves, and I believe it's probably ordered. I'm not quite sure, but it's probably, you can't have mutually recursive things without a let rec. That's explicit. It has case of an expression, just like Haskell, and you can only apply constructors, variables, and primitive operations. So you can never have like a lambda applied to some arguments. You would have to let a lambda with a name and then apply that name to some arguments. And also, you can see that when you apply things, you can only apply them to atoms, which were variables and literals here. So you also can't apply things to a lambda directly. You have to let the lambda first. And that's pretty important. We'll see later. The alts in a case expression, you can have, you can do case expressions on like primitive machine integers. That's what these primitive alts are, and they're just like literals. So you can do 0, 1, 2, match on those. Or you can do, I forget what the A stands for actually. But that's matching on like constructors of data types. And it also has a default, so in STG and core, all pattern matching will be like fully elaborated into splitting trees, and you'll never be in a situation where you have to do them in order, because all the ordering of patterns and like overlap will be resolved by the time you get there. So actually, I don't know if we have a default case in any of the code I've written, but if we did, GHC writes it out first, even though usually you'd have to write a default last in Haskell because it would overlap with everything. Oh, and also there's this little variable here in the case, after the of, and that always refers to the evaluated version of this expression that you put in the case. So if you had like an at pattern to match in Haskell to match like the whole of part of a pattern, or the whole of a pattern that you're matching on, this would be how it gets translated. It would be named by this variable, the whole expression. So the important part about all of like the invariants I mentioned was that STG has a very regular semantics for, you can like look at the code and it will sort of tell you exactly how the execution is going to go, which is a little unlike Haskell, I suppose. So,
I have a question.
Oh.
So are the lets lazy or?
Yes.
Okay.
So there are lets in core of primitive operations. You have to turn on like a flag to have it displayed that way, and those would not be lazy. But normally let implies laziness, yes, because well, you'll see it'll build a closure. So all application in STG and core is a tail call. So when you see f applied to 3 variables, it's jump into f with these 3 variables on some kind of argument stack. Or if you call a constructor, it's going to jump to that constructor code with 2 arguments. And this means that function calls never use any stack in like the core language, and that's pretty much true of Haskell too. They're all jumps for function calls. There is kind of an argument stack in the abstract machine model, but that's not the stack that gets overflowed when you get a stack overflow.
Yeah, so I don't get what you just said. X, Y, and Z are on the stack, or are they not on the stack?
They would be pushed on some kind of argument stack, yes.
And then you jump.
Yeah, so there is a stack.
Yeah,
So you push X, Y, Z on the stack and then jump to F.
okay. So,
But it doesn't like use stack frames for function calls. Like jump, you can, it's got tail call optimization basically.
Okay.
And all functions are tail calls.
okay.
Okay, and case is what actually uses like these stack frames and will eventually overflow your stack. So when you go to evaluate a case, you basically push continuations on the stack with like all these branches, and then you go to evaluate E, and then eventually you'll like decide that you're done evaluating E, and you'll go back and start popping the stack to go to one of these branches. So that's how stack overflows happen, is if you get too deeply nested in these cases, basically. Another difference from Haskell is that case always evaluates the thing that you put in, in the discriminant of the case, I guess. So you can write seek this way in STG. Seek has no free variables. It's not an update closure. It takes 2 arguments, and it does case analysis on its first argument, doesn't care what it is, and then returns its second argument. And that will ensure that both are evaluated by the time seek is done. I guess I should say it's not, GHC will reorder cases, just like seek doesn't give you a guaranteed ordering. It just says like, by the time the result is demanded, both of these things will have been evaluated more or less. So you don't necessarily know that cases won't get reordered, but whatever it decides, it will evaluate them in that order, I guess. You have to look at like the optimized output to tell.
So it more or less gives you a partial ordering on evaluation rather than a total one, or basically
Well,
a dependency graph?
So by the time you're at this level, it's a definite ordering because it's just kind of, well, I guess I can't say that because some lower level might permute things too, I guess. Like GHC will compile to core, and then it'll do a bunch of optimizations, and it might reorder the cases. And then like the final ordering it gets could be different from the original ordering as far as evaluation is concerned. So I guess if you wrote something at this level and then passed it to GHC's optimizer, it would reorder things, maybe. But the final ordering would be whatever order it actually does, if that makes sense.
So if X is open bay doors and Y is send the missiles, can you send the missiles before opening the bay doors with this code? If you have some optimizations?
Yeah.
Okay.
That's why you don't rely on seek to force order.
Yeah.
Seek just says that that if you demand Y, X will also be demanded. It doesn't say the relative order of X and Y.
Okay.
What was the question?
He asked if these had side effects, X and Y, could you be certain that they would happen in a certain order? And like, if you saw this as like output of the simplifier, you probably could, but if you fed it into the simplifier, you couldn't be sure of that. So like, you shouldn't necessarily take this as the definition of seek, I guess, but...
Well, seek doesn't force order. pseek does.
Right. So that's why you shouldn't take this exact code as the definition of seek, I guess.
Okay.
What you eventually get could be in a different ordering.
Yeah.
So, let allocates things, unless the thing that Paul mentioned happens. But generally, let allocates things. Basically, closures. So, I mentioned these lambda forms earlier. So this let block here allocates a closure named v1 that captures the free variables w and x and takes arguments y and z and does some stuff.
So I'm sorry, I'm asking these questions. What does it mean to capture variables if they're not arguments? I mean, a lambda capture.
Those are free variables. So the body of this will refer to w and x as free
It's
variables.
not allowed to talk about any free variable that's not in that list.
Right.
Okay, so
Well, that's
the
not
way you're
true.
using
Well,
the word
yeah.
captures is confusing me.
So closures capture values as free variables, right? Is that
Okay. Okay.
like this is the syntax for building a closure with free variables w and x, and then what gets packed in the closure will be whatever w and x are in scope here.
Okay.
And the second one only packs w.
Oh, sorry. But the N just means, what does that mean again?
That means no update. So when this goes to be evaluated, for lazy evaluation, sometimes if there's a U here, it'll push an update frame, and then when that goes on, that's like a stack frame, and then when it starts going back through the stack, it'll write back to the closure with the value that it computed. But for reasons I won't get into, anything with an argument.
Yeah. With any arguments, it doesn't ever make sense.
Yeah, you never have an update closure if you have arguments. And I don't think I'm going to talk about lazy evaluation today. Anyway, so.
That seems to be relevant.
What?
The list before the no update need to be relevant, or can I overestimate what's inside of the question? Does it need to be tight? Do I?
The list of free variables?
If it's not tight, you just wind up with too much crap in your closures.
Yeah.
Right.
I agree that it's too much. I'm just curious as to whether it will break something.
I don't think it.
Semantics of STG if I have.
I don't think it would break anything. It would just be carrying around extra stuff. Oh, and
Your garbage collector might suck.
well, yeah, it'd be bad for the garbage collection.
I'm
But
sure we've done for all kinds of reasons. I don't think it's a good idea. I'm just curious.
the other rule is that top level bindings don't have to be mentioned in the free variable list. Only local things are absolutely required. Sometimes it will decide to put top-level bindings in the free variable list, and I can't explain when it would do that, but it would sometimes, I guess. That's specifically mentioned. And this differs a little bit from the STG paper, I think, but whenever you call a constructor, at least pretty much whenever you call a constructor, that is also allocating. So in this example here, we have a function that takes one primitive integer, adds 1 to it, gets the value, and then builds a boxed integer with that primitive integer in it. And that will allocate like a heap pointer for the integer.
Wait, are case expressions how all evaluation is done?
What?
Is case expressions how all evaluation is done?
Yes. Because you can't put complex expressions anywhere else except like the body of a lambda form or in the discriminant of a case.
Okay.
It has a bunch of unboxed types. So these are signed integer types. Like these are machine words. This is signed, this is unsigned. Double float are the usual double and single precision floating point types. Char is a primitive, like Unicode code point of some sort. It's probably like a 32-bit integer, maybe 64, I don't know. And then the other special thing you're going to see is an unboxed tuple, and that lets you return multiple values from a function without heap allocating like a tuple structure. So it's like return multiple arguments on the stack or in registers or something like that. And these are important for avoiding allocation, and more or less, if you have like a tight inner loop, you don't want to be allocating stuff in it because that's slow. Let's see. So here's some examples of, I have the map function written in a way that you can write it. And here is the equivalent STG code. So it says that map is a top-level binding with no free variables. It's not an update because it takes 2 arguments, f and x's. F is the function, x's is the list here. And then it does case analysis on x's. In the nil case, it returns nil. In the cons case, it lets 2 closures, builds 2 closures. One is for f applied to the first element of the list, and the other is for map f applied to the rest of the list. And these are update closures, so lazy evaluation will happen, and it'll only compute these once. And then it builds a new list with those 2 closures that it just built. So,
Can you speak a little more about the U versus M? Or just like, what do you mean by this is lazy now?
U, so
one way to put it, if that was an in instead of a u, you get called by name instead of called by u.
right. So N means every time it gets executed, like exactly the body of this is going to get evaluated. U means the first time this gets executed, this f of y is going to get evaluated, and then the result is going to get written back to the address that this closure is at. And then all subsequent evaluations of it are going to refer to that already computed thing. So that saves work.
Gotcha.
And that's the difference between lazy evaluation and call by name. Okay, so here is another way of writing map. We've done the static argument transform on it. So instead of passing along this f every time, we write a little loop in the body that has like f as a free variable. So here is the way that you write that in STG. Map is a function that takes 1 argument, and then it we have to use letrec now because go is a recursive function, and go captures f and itself because it's a local variable. So it has to say that it captures a reference to itself. And it takes one argument, does the same case analysis, and then this stuff is pretty similar to the other thing. It builds two closures, update closures, one with f applied to y and the other with go applied to the rest of the list, and then builds a console with those two closures.
How does SCG know that that go is that go and not some other go that might have been let above it?
That's how let rec
Okay,
works.
so just,
Yeah, if it were let, then this go
okay.
would not be this go, it would be a go above it.
Sure, okay.
Although, unless you use a certain flag, it pretty much makes up unique names for everything, so you would never have that confusion anyway. But
Okay. Makes sense.
Does GHC automatically do that optimization sometimes? Or
no,
no, never.
there's a flag you can pass that will make it do that optimization, but it's not on any optimization level by default.
What are the calls again?
No, that's the static argument transform. Full laziness is something else.
Can you also give a quick explanation of why this one's faster? I mean, clearly there's fewer arguments.
It's not necessarily faster.
Okay.
But, okay, so I guess...
I know people sometimes do it to make their code faster.
Okay, so the first, this is the first actual optimization lesson. Sometimes code like this is better because when you have code like this, what can happen is you can mark map as inline, and then this loop will get inlined to wherever it gets called, and then the loop itself will get specialized to the specific f that it's called with, and that can be way better than this version.
Yeah, because this version of map can use F strictness information and all of that.
Right. Yeah. So like strictness analysis, all kinds of stuff gets better when you can like inline and specialize your loops to a specific higher order function.
Whereas
It's kind of unfortunate that higher order functions are slow, basically. They're way slower than like specializing your code to the specific implementation of a higher order function, at least in GHC.
And in the previous version, it can't inline map? Or it won't inline
Yeah, it-
map and then inline up?
It can't usefully inline map, at least. Like if you tell it to inline by using a inline pragma here, it will do some really weird stuff, and it'll like unroll the loop and like insert an unrolled version of map.
Once. Yeah.
I might unroll it like several times, but that's not going to be like good code.
Yeah.
Okay, so before we dive into the actual runnable examples I have, I'm going to talk about some of the optimization tools that you're going to see. The first is bang patterns. You turn them on by using a language pragma that says bang patterns, and they look like this exclamation point in front of a variable. And what this says is before the result of foo is evaluated, x should be evaluated. So it's like a seek, and they're not always necessary. GHC's strictness analysis is actually better than people tend to give it credit for, but a lot of it depends on like inlining. So like if you have fold L inline to where it knows that it's being run with plus, it will know that plus is strict, and like that loop will get, it'll run the same as if you did fold L prime, which is strict in the accumulator, but that inlining has to happen for it to know that, because regular fold L is not strict, and it would have no way of knowing that. So these bang patterns allow you to force things to be strict, even without like that kind of inlining or whole program optimization happening. And then there's a few pragmas that tend to be useful, and I'm going to use in these examples. First one is inline. This tells GHC to definitely inline foo. So it makes sure that it is able to do that, and at every opportunity it will inline foo. I guess one thing I should mention about that is, so you can have like a choice in STG of like, this takes one argument here. It could take 2 arguments and then apply go to the second argument. And that affects inlining. So GHC will only inline, and like it goes all the way back up to this definition here. I gave 1 argument, I could have given 2. And GHC will only inline until it's saturated on the, or it'll only inline if you've saturated all the arguments on the left of an equal sign. So that's important to keep in mind. Another pragma you can tack on is specialize, which tells GHC to generate and optimize a version of a function that has some polymorphic types instantiated to the specific type. So like if foo is A to A, it would build a specific int to int foo, and then it would create these rules for whenever you call foo with this int to int type, it would use the specialized version of foo that it had done more optimizations on. And then final one is inlineable, which it tells GHC to do a lot of so inline, okay, there's these interface files that GHC generates when it compiles a module, and when you mark something as inline, it will store the code for the function in the interface file so that it can like shove it into other modules. That's the only way it can inline across modules. So inlineable will do that, but it doesn't tell GHC like definitely inline this everywhere. It'll let it like judge for itself whether or not to inline. And then the other thing that it does is anytime you call foo in any other module, adding a more specific type than foo, it will try to generate one of these specialized pragmas for foo locally, and then like do all the specialized stuff, the optimization. And so that can be better than just straight inlining, because if you inline into 5 places, it'll have to do all the optimizations in 5 places, and your code will get bigger. Whereas inlineable might generate one optimized version that's just as good, and then use it in those 5 places, but do it using information at the call site instead of at the, like, if you use specialize, you have to put all of the, you have to know ahead of time all the special types that you want it to be optimized at, whereas inlineable can do it based on use. So now we're going to move on to the actual code that can be run. So I have a few examples here. So here, my first example actually came up. I was helping someone with list fusion, which is where you take like compositions of functions on lists and you rewrite them to not generate intermediate lists. So so I have 2 functions here. So there's 2 ways you can compose filter and reverse. You can filter first and then reverse, or you can reverse first and then filter, and pretty much it gives you the same answer. But if you think about it, if you filter first and then reverse, you're generating a small list and then reversing a small list. And if you reverse first, you're reversing a large list and then generating a small list. So this one should do less work. And if we run it, let's see, 0. So this is reverse filter that takes 1.7 seconds. And, oh, that's the wrong one. Filter reverse takes 3 seconds. So filter reverse is clearly doing more work. And, oh, I forgot to mention something. If we look at my Cabal file here, I'm using this RTS option -s, which it makes GHC dump out a bunch of garbage collector info. And the one that I'm going to be looking at is allocation, because I mentioned earlier that like doing allocation in a tight loop is bad. So this gives you like a general picture of how much stuff you're allocating. It's not like peak heap usage, because this says like 2.6 gigs here, and it doesn't use, this runs in like constant space, but it just generated 2.6 gigs of stuff and then like threw it away immediately, basically. Let's see, this one did 2.6 gigs and then the other one did 1.8 gigs. So the one that runs faster and does less work also does less heap allocation. Oh wait, that was 2, sorry. 2.4 gigs is the efficient one instead of 2.6. So these were the unfused versions, because in the current version of GHC there's no fusion between reverse and anything. So you might be interested to hand specify a fused version of those things. So I have those here. So this is the filter first, then reverse fusion, and so it does that static argument thing, and then for the empty list it returns an accumulator, and then for the non-empty list it tests the predicate and then calls itself recursively with an augmented accumulator based on the result of that predicate. And then the only difference between that and the filter after reversing version is that instead of putting the test here, we call the loop recursively with a just an accumulator that does the test. So if we run these now, let's see. So this is reverse after filter fused version, and that does 1.8 gigs of allocation and takes 1.6 seconds, which I think that was, so it's not any faster, but it does less allocation than the original. And then the original opposite one was 3.2 seconds and did 2.6 gigs of heap allocation. And this one is 3.4 seconds and does 2.4 or 2.5 gigs of heap allocation. So that one actually got slower when I fused it, which is interesting. And you might think like it's doing almost as much heap allocation as the original one did. So you might think we got rid of the intermediate list. Why does that happen, right? So if we go look at the intermediate stuff, so this is filter after reversing.
I have
If
a
you,
question.
yes,
Roughly, what's the selectivity of the predicate that you're filtering with?
half.
Okay.
I did even, and it's like 1 to 20 billion or something like that. Oh, I forgot to show you the driver. Sorry. Yeah, here. So I have this big list, 1 to 20 billion, and then these first 4 driver functions just call it. It filters even things and then sums them all, and just does that with all 4 functions. So if we look at the core here for the fused version of filter and then reverse, we can see that it looks very much like, actually it looks very much like the source, I guess, in that it recursively calls, so this is a type argument, this is the predicate, this is the list, and then it builds this recursive loop that just calls itself with this complex expression, which I said in STG, you're not allowed to call functions with complex expressions, but in core, it doesn't have that restriction. But the important thing to remember is that STG does have that restriction. So if we look at the STG, here's the fused version, and here's the cons case. And you can see that it does a let, which allocates things, and what it's allocating is this test against the predicate and then returns either the accumulator or an augmented accumulator. Apparently, GHC's version of STG uses square brackets instead of curly braces. So basically, we got rid of the list allocation, but instead we are allocating these closures that delay doing the tests until it gets looked at. So you're building as many things as you would build with the list. You're just building different things. So, and that turns out apparently to be worse performance or speed-wise and only slightly better memory allocation-wise. And if we go look at, here's the fused version of reverse and then, or reverse after filtering, and you can see that it, in this cons case, it does a case of the predicate and then, so this doesn't have to do any allocation. It just tests the predicate in a case immediately and then calls itself recursively. Well, it has to build a bigger list if it should, according to the predicate, but it doesn't do allocation regardless. So that's why it's able to save quite a bit more work and allocation in the reverse first case. No, reverse second case.
So if your predicate accepted everything, would the performance still be better?
Performance of which?
The fused reverse filter. The one that ended up doing better, but it had not have done better had the random predicate, which was just true, basically.
I don't know. Let's see. You want reverse then filter, right?
And X true.
So that was 1.7 seconds and 2.4 gigs. Well, that was quite a bit worse, actually. Interesting.
You only replaced one of the predicates, right?
Yeah. Oh, right. I need to replace this one, too.
There are opportunities for factorization in that code.
Yes. All right, 2.6 and 3.2. So it's way better on allocation, but slightly worse on runtime. I didn't do, so if you go look, let's see.
I mean, it's possible that all that runtime is just the sum now or something.
So I didn't do this, for one. All right, that didn't matter. I don't know. It looks like it might be just variance too.
But I mean, it makes sense because now it's doing allocation for every single time because it's hitting the false every single time.
Yeah.
Right.
Well, it still gets rid of an intermediate list.
Right, but it's allocating something else, whatever it's allocating.
Allocated, but kind of not.
It has to allocate the output every time, but it doesn't have to allocate an intermediate list.
Is it gonna allocate the thumb for the const application? No, it's not. It's only gonna make one.
I don't think so. Anyway,
Maybe like, I don't know.
the point of this example, in my mind, was just to show that you have to be careful about deforesting lists and not deforesting to a thing that just does exactly the same thing with regards to like allocation and stuff. Just like in a different way. You want to actually save work, not do different work.
So the different work, just so I perfectly understand, is creating a thunk, right?
Yeah, it's create a thunk that when you inspect it, evaluates the predicate and then returns and like writes back either the same accumulator or the accumulator plus an element.
Can you go to the STG for I think reverse filter fuse? The one that has the if in the expression that's allocated.
Are you looking to see if it's an update thunk?
No, no. So, should be, what I want to see is the list of free variables.
I don't actually know if this has, which one do you want to see? Reverse
The
filter?
one that has like go of if.
What's up? It's this one, right?
It should be the one that has like. Yeah, okay.
Mm-hmm.
Does that even have that in here? I didn't look. I think it's this. No,
What are you looking for?
the list of free variables.
I can assume based on what you would, it would be the SRT and SRT, but.
I don't actually look at STG very often. I just look at core, and occasionally you have to think about how core would turn into STG, like in this example, because the core will just, like it just had the function applied to a complex expression, and you have to remember that that causes allocation. That was the other point of this example, was to point that out.
But I guess where I was trying to go is, I'm not sure if it's saying this or not, is if you had a closure with like 2 free variables, that would be pretty much exactly the same as having a const.
Yeah. I don't think it lists the free variables in this dump representation. It just expects you to figure them out.
Is the fact that you can tell me the core indicative that there isn't much, there aren't aggressive transformation passes between core and STG?
I don't think there's, I don't think there's transformation passes on STG itself.
Well, right, but when you go from core to STG, other than flattening out.
I think it's just, like making the exact allocation and stuff more explicit. So I don't think there's a big difference between the STG you'll see and the core, as long as you use dump simple, which is after all of the core optimizations have run. If you dump something earlier than that, because there's core stuff earlier than that, then there would be potentially a significant difference. Okay, so my second example was short-circuiting multiply. So I wrote this function that consumes a list, and if it ever sees a 0, it just returns 0 immediately. And I wrote it in a pretty bad way to start off with, because the big problem with this to start off with is that this accumulator is not strict, because like we throw it away in this case, right? So unless GHC does something smart, which I have verified that it won't for this example, it won't like keep this accumulator evaluated at all. And then I have a version here where it's I use bang patterns to ensure that it gets kept evaluated. and I have a version here that's marked inlineable, and I did not tell it to make the accumulator strict. So,
I have a question about that.
Yeah.
Is it, would you just need, bank, to go back to the source?
Oh.
Would you just need a bank pattern on the, it's line, but on, basically on the equation?
this one, you only need it on the first one.
I thought you don't need it on the one for return 0.
Well, it has to go through the first case first, so it'll have already forced it.
Yeah, it has to do these in order anyway, or it will do them in order.
Yeah.
So if you put it,
I was curious if I just annotated, the 0 case.
oh, yeah, that would
and with
probably
this
work too.
analysis, like,
Yeah.
take over and realize, oh, no, they're all strict, so.
I think so.
Yes, I think it would. I didn't test, but I think it would.
Well, if it's not forcing the first act, then, and it does the next pattern next, it can still reject on the 0 didn't match the card, but it would still need to force the act if that were the thing. So I don't know whether that strictness analysis so much as we delayed forcing act one step when it wasn't empty.
Yeah. but
Well-
for the function, it's not there, or, yeah, it's not there. It could think it's lazy, even though it is actually.
Yeah.
To absorb.
That's the one case that is not strict in that value, I guess, or it's like the hole you'd have to close to make the whole thing strict. So
Yeah, assuming once you've plugged that hole, GHC strictness analyzer should be smart enough to figure out that thing is
Yes.
strict enough.
yeah.
And this is trusted GHC.
So I have I actually have 4 things. One calls the regular product function. One calls the short circuit one calls the strict version, and one calls the specialized version. So that's 4, 5, 6, 7. So regular product runs, and I'm calling it on that list of 20 million things. And there's no 0 in it. So I'm feeding it like a worst case scenario. Because it also doesn't, it's a list of integers, but it doesn't check if the accumulator is 0 either. So if it overflows all the way to 0, it's going to keep going anyway, unless it sees a argument that's actually 0.
So the product is 0, not because there was a 0 in there, but just because you have enough terms that give you enough 2s.
Yeah, it's like 20.
So you have enough factors of
product
2
up to
that
20
force you to
million.
0.
Yes.
Yeah, 20 billion factorial is a little big.
Yeah, but that has a lot of factors of 2 in it, and therefore you've saturated and got 0.
Right. So
But not because of the...
So that ran in 0.2 seconds. That's the regular product. The dumb one runs in
It's a great optimization, that short circuiting.
6 seconds. Yeah. I actually thought about making an example where I could see how small a list I could get before. Again, putting a 0 in was actually worse than multiplying 20 million elements. Let's see. So this is the strict one, right? And that ran in still slower than the regular product. And the reason is that it's much better if you specialize to integers, and just marking those things strict does not specialize the code to an integer. It's still calling, it's not building a giant nested func of multiplies, which is really bad, but it's it's not working on unboxed integers, which is what the purpose of this example is. So let's see. Oh, actually, you can't see it in this file, but actually, inlineable is actually better than specialize in this case for reasons I don't really understand. Well, I know why, but I don't know why GHC doesn't do the same optimization. So if we look in this, like, if we look at the strict, this is not going to inline, and it's just working on like arbitrary num eq stuff. So that's going to be pretty slow if you're just trying to multiply integers, which is why it's still slower than the built-in product, which is going to get, I'm pretty sure, specialized to integer. So if we look at the executable dump stuff, oh, it's the wrong file. Oop. So, GHC actually, so remember that I didn't mark anything strict in that inlineable version, but GHC actually does this thing where, so here's the spec pragma for the specialized product function. So it says that if you ever call product SCS specialize with @integer, then it's instead calls this specialized product SC specialized function, which is here. So it uses an unboxed accumulator. And it does this thing where, oh, actually, so, okay, what it does for some reason is it generates these two specialized things where it figures out if you're calling it with like an already evaluated accumulator, and then once it knows that it's evaluated, it just keeps it evaluated instead of ever allocating funcs. And if you just specialize it, it doesn't do that for some reason.
Yeah, isn't this just effectively a worker wrapper?
Yes. So, but it's a smarter worker wrapper than I thought it would be.
Every time you said integer, that's, and then it's equal, right?
Yes, int, machine integer, like
Really, really
64 bits. Yes, 64-bit integers. Yeah.
This is a slight difference to our question earlier about putting the bang in a second case. Since you don't know plus is strict, it can still be lazy.
Right. Yeah, for like the completely polymorphic version, yes. It doesn't know that it's strict at all, so it can't do like, yeah.
The strictness amount, we say if we put a bang on the second case and left all the others, it would know the accumulator strict, but the third case it wouldn't know because it's x plus half, plus can be not strict.
Right.
So that's why I use bang patterns and use plenty of them.
But this is actually,
Very subtle.
I was surprised how smart this is, because if we look here, so the first one rewrites the specialized thing to the specialized version of it, and then the second one rewrites the specialized version when called with a like known boxed, like already evaluated value, and it calls this this other version that only
Takes the
uses,
unboxed value.
Yeah, that's
Yeah.
normal worker wrapper.
right.
But it doesn't know this.
But
is
it
not the
it knows, like, I wouldn't expect worker wrapper to work if, like, it can't do that on lazy. If it's expected to keep it lazy, like, it isn't strict in that argument, right? So in this case, it's making a decision to, if it's already strict, keep it strict anyway, instead of ever making it lazy, even though technically it kind of could.
Okay, I see why you're thinking, okay. But yeah, it does that.
Yeah, so it does something fast, faster than I might have expected. And this just like, I made up this Vim highlighting file, and it highlights all boxed integer types in orange because those do allocation, and it highlights unboxed things in blue because those are good and they don't do allocation. So when you have like a tight loop like this with an accumulator, you want to see the accumulator being unboxed because that means it never, like, the other one, like if it looked like this, if this was a straight loop, it would have to, for every element of this list, it would peel this apart, do the multiplication, and then build a new pointer keep allocated value with that result, and then recall itself, and then do that every time. So it would generate a lot more garbage and be a lot slower. So when you have really tight loops, you want stuff that looks like this. Any-
Should probably wrap up.
Okay. All right, I had one more example.
Yeah, that's fine.
Okay. So my last example is Quicksort. So I have this Quicksort function that I kind of stole from vector algorithms, which I wrote. It's just, it doesn't really matter what it is. I mean, it's Quicksort, but you don't have to understand how it works. And then I marked it with specialized. And this Quicksort version takes a value that is the less than comparison for the Quicksort. And then I have another version that instead uses ORD. And both versions I marked specialized to words. So if you pass it a vector of words, it'll use this specialized word version of the Quicksort function. And let's see, these are 8 and 9. Oh, and I'm passing it big vector is 0 to 100,000 sorted already, so that's the worst case you can pass the Quicksort. So it's pretty slow. So when you use the parameter, this is like equally, specialized. So it takes 9 seconds, and you use a parameter. And if you call it with a class, it takes 1.8 seconds. So why did that happen? And the answer is, I mentioned earlier that so I have this static argument here. I mentioned that it's really good if you can inline the function and specialize the loop body to this specific comparison function. But these are not marked inline, and they're too big for GHC to decide to inline them by itself. So this is calling this higher order word function, or function on words, indirectly every time. And it has to these are unboxed vectors, so what it has to do in every step of this loop is it pulls a raw machine word out, builds a box, passes it to the comparison function, gets a result, and then sticks it back in the array. So that's really bad. But when you use classes and you specialize to word, GHC knows the value of less than for this word dictionary. So it specializes all the code to that specific comparison function and generates it does all unboxed stuff. So if we go look at the dumped stuff real quick. Let's see, Quicksort. So the reason I used word is so that I can do this. So you see orange words in here, and there is no word hash anywhere in the file. So that's bad, because it means that all of the words in that file were boxed. And if we go to class sort, there are now word hash stuff in here. So that is running stuff on the machine words without doing any allocation of the words or anything like that. So that's why you get that almost order of magnitude speed up. And you'll notice this is a lot of code. 2,000 some lines just for that small Quicksort function. So I did a lot of this kind of optimization on vector algorithms, which does Quicksort, all kinds of sort stuff. So basically I guess my advice is just to look for this kind of stuff and look for all the cases. So one bad case here is this is the partition function, I believe, and it returns a boxed integer. So that's technically like for every partition, it has to allocate heap for the integer it returns for like where to like do the pivoting. So that's not as good as it could be. And my goal for vector algorithms was to like just like do searches, try to figure out what code was what, and eliminate all of those boxes. And it generally works pretty well as long as it doesn't get broken by new versions of GHC, which happens quite
How
a
do
bit.
you eliminate the boxes in general?
So
Inline or?
for like this example, you have to, inlining is basically it. So to eliminate this int here, I think you have to inline partition into Quicksort because that's the only way it can avoid allocating at that boundary.
Can you use a pragma or
Yeah.
do you have to go back in?
Oh, yeah, you use pragmas. I use pragmas. That would be terrible if you had to manually inline into one
Right.
mega function. I mean, it's still bad, but it's not as painful as it could be. So I guess that's it. And then I have this last slide of resources. So this gives you the URL for the GHC Users Guide. Here's the full STG paper if you're interested in reading more about it and you want to understand more about the sort of abstract machine model. Yeah, lots of GHC people work at Microsoft Research.
Really?
Yeah, or they used to.
We have one of them left there.
Yeah.
Yeah, so this is the highlighting file I used for those core files. It was supposed to be a lot more intelligent, but it's surprisingly hard to parse those with Vim. And this is the, whoop.
Never solved that problem in darks where it was, for medium size it'd be fine. If your project got too big, it would like trying to merge would go off the la-la land and sit for a week.
They mostly fixed that with Darks too, didn't they?
I've never really had problems, but
I was looking, years ago, I was looking at that.
Yeah, it was around Darks 2 that they, if you use the Darks 2 repo format, then that actually is basically fixed these days.
Theory of patches.
anyway, you had a question?
So if you're writing a library that somebody else is supposed to use, is it on you to put in all the inline fragments?
Yeah, basically. Yes, basically.
So conversely, if I have a library that I'm using who's offered to not put in inline fragments,
You're out of luck.
Yeah.
You have to send them patches or rewrite it or, yeah.
Or at least convince them to do inlineable at least or something.
Yeah, like the problem is if they didn't put inline or inlineable, there's just no way that GHC can, it doesn't have the information to inline it into your code by the time it gets to your code. So they have to have, unless it just decided that something was inlineable itself, which sometimes it does, but they have to be pretty small for that to happen. So unless they took measures to allow you to do that, it's not going to happen. So you just have to, you have to contact the author or rewrite it yourself or something.
I have a small question, I can just find out later, but if you don't know. Do you know if they switched, like back in the day, I don't think Inlineable has been around as long as Specialized and the other stuff, admittedly Specialized.
Inlineable's really new.
Yeah.
Yeah, it's
so
pretty new.
Did they change the GHC source to not have like 16 lines of Specialized after everything to just be Inlineable, or do they still have it?
I doubt it.
I doubt
Like,
it too.
there's lots of really old stuff. Like there's tons of code in like base that
Yeah.
doesn't need to be written the way it is anymore because just the optimizer is good enough to do it
Yeah.
for you, but nobody's revised the code.
I just cut through like 20 lines worth of specializes for lift dem variants and a whole bunch of other stuff with Herbert and a couple other folks just today. So I know there's still a whole bunch of them in there.
There's even
Actually,
stuff.
that's it.
There's even stuff where people like manually use unboxed integers.
Yeah, I remember when I started,
And-
that was the thing to do because it wasn't good enough to do it.
Right. That's like pretty much no longer necessary.
No, yeah, it's not a good thing to do ever anymore.
Yeah, but it's still in there. So, anything else? All right.
Thank you.